Okay, here we go. Here is the graph of an exponential function, e to the x. Just a reminder of graphing exponential functions. If you have 3 to the x, 4 to the x, 5 to the x, they all have a vertical asymptote at y equals 0. They all go through 0, 1, because if you ever have an exponent of 0, 2 to the 0, 1, 5 to the 0, 1. This is the graph of e. It has e to the 0, which would also have a 1. Now the crazy thing about e to the x is if you draw a tangent at any point and mark the derivative or the slope of that tangent, look what happens. That's crazy. So when we have special numbers in math, like pi was related to a circle. People were trying to figure out how many diameters fit around the edge of the circle, and they got 3, it's more than 3, then they were like, it's close to 3.1, no, it's close to 3.14, and it got closer and closer and closer, and they come up with this weird number, pi, for how many diameters fit around the circle. And then in derivatives, they're like, oh, with exponential functions, the derivative is really, really close to itself, but not exact. Maybe there's one number that works out perfectly to be exactly the same as its function, and it happens to be e, which in some ways is going to hurt your brain, because you know how, oh, that's the wrong one. You know how when we did derivatives, like some of our rules are keep something the same and do the derivative of the other one? And now when we do the derivative of something, it actually stays the same. It's just there to, I think, mess with your brain a little bit. So yes, if you've got e to the x, the derivative is e to the x. But now we can add all the chain rule, product rule, quotient rule stuff involved with e to the x. Does a number in front? Okay, so sometimes students are like, do I have to use a product rule if it's just a number in front? Or can I just use regular derivative rules? Okay, we only have to use a product rule if the two things each have their own unique derivative. A 5 is just a constant in front, so you can just leave it there. The derivative of 5e to the x will just be 5e to the x. Okay, not too bad. If you had to work backwards with an e to the x, it also would be not bad. The original equation would have had a 4e to the x, and this would have had an x to the 5. Can you see that there would have needed to be a 3 out in front in order for that 15 to be there? And this is a function that would have that as its derivative. Of course, if you wanted to add a number at the end, plus 3, it's your favorite number, you could. So this question right here says, find the equation of the tangent to y equals e to the x at 0, 1. So if we go back to the diagram that we had up before, when I bring it right to 0, 1, what we're trying to find is what is the equation of that red line. Equations of lines are y equals mx plus b. To find an equation of a line, you always need two things. You need a point, which we have, 0, 1, and you need the slope. we find the slope from our derivative. So we take y equals e to the x. The first thing we're going to do is we are going to find our derivative, and the derivative is e to the x. We are trying to find it when x equals 0. It's pretty obvious that you plug in 0 and you'll get 1. So then we know that our slope is 1. So you get your slope from your derivative, and now all we have to do is plug everything into y equals mx plus b. What do we know? We know the slope is 1. We know that when x is 0, y is 1. And you can solve for b. And maybe you noticed in this question, if the point was 0, 1, you already knew b as well. But sometimes you only realize that after you've done all the work and go, oh, I could have done this just by seeing that the point is 0, 1. But now, as a final, we can write the equation of this line. The slope is 1. Y-intercept is 1. There's the equation of the tangent. Next, we look at the graph of the natural log. Remember, the natural log graph is an inverse of an e to the x graph. So it has an asymptote at y equals 0. Same sort of shape. Instead of 0, 1, it has 1, 0. And when we take this graph and look at the derivative, we have to think back to grade 12 pre-calculus. Did we ever see this shape of graph before? And the answer is yes, but this is only half of it. So you had a graph that looked like this shape before. It happens to be, oh, I'm sorry, I'm skipping ahead. I thought the log one was next. Here. So I just changed the graph here to a 2 to the x graph. And if we do, like, this is how they probably were like, when they were looking at the derivatives, they're like, oh, it's so close. It's so close to matching up perfectly with the other one, but it's a little bit off. What if I changed it to 3 to the x? Oh my goodness. Ooh, 3 to the x is really close. And so the derivatives of every other power become almost the same, just off by a little bit, and the little bit that they're off by is the natural log of b. Now, a little bit of playing around with this. Okay? If I have y equals 3 to the x, and I want to play around with this, and what I want to do is, instead of writing this as y equals 3 to the x, I would like to write this as y equals e to something that's equal to 3 to the x. So I'm going to play around with this equation. If I have y equals 3 to the x, and this will be a little review of some of your log laws, and I take the natural log of both sides. Taking the natural log of both sides would give me the natural log of y equals the natural log of 3 to the x, which would allow me to bring the x out in front. So one of our log laws says, if you have a power inside of a logarithm, that power can come out in front. Now that I've taken the log of both sides, I can undo that taking the log of both sides by making or putting both of these as powers of e. So if I do this on this side, and the same thing on this side, and since e and natural logs are inverses of each other, just like square rooting and squaring, whenever you have them together, they cancel each other out. So you square a square root, you get rid of the square root. If you have a natural log in the exponent of an e, that'll just simplify just to be back to y. And we get this. Okay? So what I did is I changed 3 to the x, right, to a new form. 3 to the x is now equal e to the x natural log of 3. Just like changing fractions to have different forms, I changed 3 to the x to have a different form, but now it has a base of e. The reason it's nice that it has a base of e is I know that derivative. What's the derivative of e to the x? The derivative of e to the x is exactly the same. So I want to find the derivative of this. It is going to be a chain rule, because inside the e to the x, we have a number times x. So how do we do a chain rule? Again, we have to decide what function is inside, what function is outside. The outside function is the e. The derivative of e to the x stays the same. So derivative of the outside, keep the inside the same, then we're going to need to multiply by the derivative of the inside. And this part, if we go back to the beginning, that was just 3 to the x. So what we just did was we just used a specific example to show a technique of how we could find the derivative of 3 to the x if we didn't know this rule. And in fact, by doing it that way, we have sort of proven how this rule works using the derivative of e to the x. So the derivative of any other base that you have will also be the same, but you're going to have to add a natural log of that base afterwards, because it's not quite the same. So when we go through these, dy dx, well, this will stay the same times natural log of 3, and this one, bring the 5 on in front, will be 10x. And now we get to see the log graph. And the derivative of that log graph that we drew earlier is a 1 over x graph, but only half of it. Do you remember the graph of 1 over x? A 1 over x graph had two asymptotes. And look like this. The derivative of the natural log of x is only this half because the domain of the natural log of x is only when x is bigger than 0. So its derivative only exists right for x bigger than 0. So same rules, if you just have a constant in front, that constant would stay. This derivative would be 5 times 1 over x. And you could write it as 5 over x? Yeah. Because this is multiplying fractions, it's like a 5 over 1. But I just wanted to show that that number gets multiplied by the derivative. 5 for any kind of constant in front just would stay, doesn't make a difference, becomes 5 over x. And similar to exponents, if you have a different base other than e, again, it's going to be 1 over x, but a little bit off. And we could do a proof of this one as well. And we could rearrange things to make this work. But it's going to be 1 over x, and you're going to add a natural log of whatever that base is on the bottom. So what does this mean? If we had, again, I'm just keeping the 2 out in front so that you can, like, trying to simplify too many things at once sometimes causes you to have problems, make errors. So that 2, yes, would go on the top. So we still have the 1 over x, but we'd also have the natural log of 7 on the bottom. For your quiz on Tuesday, I have a tiny little review sheet of the derivatives that are a little bit harder to remember, like b to the x and log base b to the x and cosecant, secant, and cotangent. And I'll let you use this on your quiz on Tuesday. I also put on the back of here some of the trig identities. They're up on the wall as well. I'm not going to take them down. So I would, it's fun to have them memorized for sure. But if you don't have to stress about that. More important that you're able to do the derivatives. That being said, when we get into questions that have product rule and all of our exponent rules combined, in order to keep your mind straight of what you're doing, it's sometimes very helpful that you have everything memorized as you go along. But if you have a sheet that you're looking at right beside, sometimes if you can recall it quick, that's also helpful in doing things. So here we have f of x. We have multiplication, and in between that multiplication, there are things that both have a derivative, so we have to use the product rule. Before I start, I change that square root to an x to the half, and then my derivative will be, keep one the same, right? You keep one the same, and then you change the second one by doing its derivative, which also stays the same. Plus, keep the other one the same, times by the derivative of the first one. So I'd like you to try the next couple on your own. I'll put up the answers in a bit. Now you wouldn't have to simplify it. I did a little bit of simplifying here. But if you have that first line, perfect. If you wanted to simplify it and factor something out, you could, but not necessary. Quotient rule. Whoa. Another quotient rule. And I didn't simplify this time, even though you could have easily taken out an x out of that part. And then factored out. Oh, this one is tempting to simplify. But we'll leave it like this. All right, check the next one. You first change that to x to the half, then it's a chain rule, because the x to the half is inside the e. We do, and before, the outside function and inside function were easier, I think, to tell. They get a little bit more tricky. So now the outside function is the e, because x to the half is inside of it. It's where the x was. So we do the derivative of the outside function, which stays the same, and then multiply by the derivative of the inside function. Product rule, keep one the same. Derivative of the second one, but do you notice the second one is a chain rule? Because there's a 5x inside of the natural log. So we do the outside function natural log, that'll be 1 over x normally, but 1 over keep the inside the same, multiply by the derivative of the inside. Plus, now keep the second one the same, and multiply by the derivative of the first one. Another chain rule. So we have a 1 plus 6x inside of natural log. So the outside function's natural log. Its derivative is 1 over x, so we write 1 over, keep the inside the same. Then multiply by the derivative of the inside function. It is a product rule. Keep the first one the same. Derivative of the second one is a chain rule, because there's an x to the 4 inside the e. So we do the derivative of the outside function, which is e, keep the inside the same, multiply by the derivative of the inside function. And in this case, if you wanted to simplify this, no, never mind. We won't simplify it. But you could factor out a 7 and an e x to the 4 out of both of them. Okay, first step in the last one here. Change it. I would probably make this a third and move it to the top, because the top number is just a 2. You could use your quotient rule, but you're going to get a 0 in there, so you're going to write way too much stuff. Better to change it to a negative exponent. And now we have a chain rule. An inside function also has a chain rule. So how do we walk through this slowly? Well, the outside function is the negative 1/3. That negative 1/3 comes out in front, subtract 1 from the exponent, and keep the inside the same. Then we do the derivative of the inside, and this part is a chain rule as well. So its derivative would be e to the negative 3x, keep the inside function the same, multiplied by the derivative of the inside function.